Yeah, thanks for coming to our presentation. I'm going to hand it over to George Matthews, who's the meteorologist in charge of our office. He's going to go ahead and introduce and give you an idea of what we're going to do here today to show you what actually happened on the April 27th, which is the super outbreak. This is the super outbreak of all time. So we're going to talk about what led to this happening and show you some more information about how we try to warn for tornadoes, and then how we go out on tornado surveys and try to rate the storms, give it an intensity rating. So, George, did you want to say a few words before we get going?
Yeah, thanks everybody for coming this evening. I'm fortunate to have an event like happened back in April to have, for circumstances, to have something that a lot of people are excited to hear about. It is a fascinating event, unfortunately a deadly event as well, but just from the scientific aspect, it was a fascinating event, and I guess this may kick off in some ways for this area many years of research to come. I'm sure there's going to be a lot learned. We learned some things, but seems like we just have decompressed from the event overall, and now we can maybe start digging a little bit deeper into some of the finer aspects of it. Yeah, just to kind of kick things off, we're going to, after getting done with the introductions, going to talk about the forecasting of the event, and then the kind of active warning mode, which usually warning mode is like 6 p.m. to 10 p.m. This time it was about 6 a.m. to 1:30 a.m. With a little bit of a break in the middle of it, but and then we'll get into the damage and storm surveys and all that to wrap things up. So just like warning operations is a teamwork event, we're going to tag team here, hoping to keep things rolling, trying to we're meteorologists, and we'll hope for the best on the equipment, and so I'll kick it over to David Gaffin to talk about the forecasting first of all, then we'll get on with the rest of it. So I'll be back in a few minutes talking about storm surveys.
Yeah, I wanted to talk about some of the science behind the tornado outbreak, because a lot of times when when you're trying to explain something to people, and especially if you're trying to just simplify it and just try to keep it real simple, they always talk about, well, you had a clash of warm air and cold air, and that's why you got a big outbreak. Well, we get warm air and cold air clashing a lot, so that's really just a very simplistic way of describing this, and obviously there's more to it than that. And so I'm going to go into some of the aspects of this event that made this such a big event. And there are things about tornadogenesis we don't completely understand, so there's still a lot of things that we've got to try to understand better, because this was a very, very efficient event. A lot of times when you get supercell storms, and whenever I say supercells, I'm talking about a rotating thunderstorm. So whenever you have these rotating thunderstorms, you don't always get tornadoes, but if you're going to get a long-lived and strong tornado, they're usually the result of a supercell. So this was a very, very efficient event, because the super outbreak of April 1974, we had right around 150 tornadoes across the whole United States. And this one, I think the last count I heard was like 345 tornadoes for the whole United States. And so we more than doubled that. And the super outbreak of 1974 had always been the benchmark. That had always been the event that just greatly exceeded all the other events. If you ever looked at tornado statistics, you'd always see the super outbreak will always just skewed the statistics to the high side. So now we've had an event where we've had double that. So it certainly was an extraordinary event. And now I may end up telling you more than you really wanted to know about this event, but I'm going to try to give you the rest of the story, so that you feel like you at least understand more about what we understand about tornadogenesis. And what you're looking at right here is what we call a sounding. And you're looking at the vertical profile of the atmosphere. And the bottom of it is the surface, and then you go up, you can go all the way up to about 40,000 feet, roughly right around 40,000 feet. And the center is probably about 18 to 20,000 feet above the surface. So this is something that's really nice to look at because it gives you a lot of information right in a short amount of time. The line here that's on the right side is the temperature line. So as you can tell, the higher in the atmosphere you go, the cooler it gets. That's normally what happens in the atmosphere. And to have thunderstorms, you need to have an unstable air mass. I don't know if you ever read our forecast discussions on our website, but you'll probably see a common theme that we talk about a lot about is whether the atmosphere is unstable or stable. So if it's really warm and moist at the surface, and then the higher up you go, it gets very cold. Let's say you have very cold temperatures, about 10 to 20,000 feet in the upper part of the atmosphere, you have a big temperature contrast, and you're going to get these vertical motions started that will produce a thunderstorm because moist air wants to rise and cold, dry air wants to sink. So when it's really warm and moist at the surface and really cold and dry, about 10 to 20,000 feet above us, then it's going to switch places, and it's going to usually switch places in a violent manner in the form of a thunderstorm. So, that's one of the reasons why when we get thunderstorms, they're normally during the afternoon and evening hours because that's when we're very warm and hot here at the surface. But one thing about this event that you may or may not have noticed is that these thunderstorms continued well into the night. They went, I think our last tornado in our area of responsibility, which includes East Tennessee and Southwest Virginia and a little bit of western North Carolina, the last tornado that we had was right around 1:15 in the morning. It was up there in Glade Springs near Abington. And that was a very strong tornado. So you may be wondering, well, if we're cooling down in the evening, why did we still have we had really strong activity going on into the night? Well, it's because even though we're cooling down here at the surface, it's still cooling down even faster above us, about 10 to 20,000 feet above us. So there's still that big temperature contrast. So that's why these thunderstorms continued on well into the night. And another really important factor that really made this a big tornado outbreak, because an unstable air mass is what you need to have thunderstorms. If you're hearing thunder, you've got an unstable air mass. Okay, that's what you need to have thunderstorms. But the reason why these thunderstorms rotated is if you look here on the right side, this is a wind profile of the whole atmosphere, and these flags, they look like flags, and they're pointing in the direction that the wind is coming from, okay? And the more, if you have some lines at the end, one line means 10 knots, and then so if you have several lines, you've got 20 or 30 knots, and then if you see a triangle, that's for 50 knots. So as you can tell, I hope that's something you can see. It might be hard to tell, but we had very strong winds all through the atmosphere, and most importantly, these winds were rotating in a clockwise fashion, or the higher in the atmosphere you went, the more the winds, they changed direction in a clockwise direction. You can tell here at the surface you had southerly winds. You had winds coming from the south, and then as you went up about, it looks like about 5,000 or 6,000 feet up, then they're coming out from the southwest. You go up further, and they're becoming more westerly as you go higher. And actually, some of the surface winds, on this sounding right here, it's showing southerly winds, but we had a lot of reports of southeasterly winds. So as you can tell, looking at that profile, as you go up in the atmosphere in height, it's going to be rotating in a clockwise direction. So any updraft that forms for a thunderstorm, it's going to get a slow spin put on it. Well, in this case, it'll get a fast spin put on it because these are really strong winds going through the atmosphere. So that's one of the big ingredients that causes these thunderstorms to rotate. And then when you have a rotating thunderstorm, that's a supercell. And one thing you can definitely expect from a supercell is very large hail. And I know a lot of you from the Knoxville area are probably thinking, yeah, we got really large hail. It was anywhere from golf ball to baseball size hail. We had some softball size hail reports. So that right there, whenever you have a strong updraft, whenever the updraft is being rotated, it strengthens the updraft. And that's what ultimately causes the large hail, because you have to have a large updraft to suspend that hail up in the air. You know, eventually it's going to get so big that it's just going to fall out. But if you're getting really big hail, then you know you had a really strong updraft. Okay, so we definitely had that with these supercells. And then occasionally they'll produce a tornado, and when they do, it tends to be long-lived, and they can be strong tornadoes. But we don't always get tornadoes from supercells, but during this event it seemed like almost every storm was producing a tornado. So it was a very, very efficient event, very prolific, and that's probably going to be one of the big topics of research from this event, is trying to find out why it was so efficient at producing tornadoes, because, you know, it's the big event of our generation. Well, it's the big event of, you know, of recorded history that we have. 1950 is when they really started making it more of a conscientious effort to document tornadoes and keep statistics on tornadoes. So usually when they say recorded history, they're talking about since 1950. So, you know, it was a very big event, extraordinary event, and hopefully we don't see another event like this for a long time. You know, the only other event you can compare it to was that April 1974 super outbreak about 37 years ago. So hopefully it takes another 37 years for it to happen again. But, you know, hopefully it never happens again. But if it has to happen again, hopefully it'll take a long time for it to happen again. So that's really kind of the basics of what went on that day. And I wanted to show one other diagram. We can measure something called helicity, and helicity is really it's applying a numerical value to that wind profile that I showed you. So the higher your numbers are, the more conducive it is to producing tornadoes, because you've got not only strong winds in the atmosphere, but they're rotating in that clockwise manner as you go up in the atmosphere. So in other words, you know, if you've got really high helicity values, you're going to be putting a lot of spin on any updraft that forms for a thunderstorm. So this is from 0 to 1 kilometer in the atmosphere, so anywhere from like the surface to 3,500 feet. If you get helicity values of 100, that's considered very good for tornadogenesis. And in this diagram, I don't know if you can see it too well, but we had a lot of values of anywhere from 4 to 500. So 4 to 5 times what's considered good enough to produce, or I shouldn't say good enough, but, you know, is conducive. You know, values of 100 are considered very conducive to producing tornadoes. So we had extraordinarily high values of helicity, and that really kind of tips us off that this could be a big event, be a significant event. And, you know, I don't think anybody knew ahead of time that it would turn out to be the event, you know, the big event. That's really hard to know. It's really kind of impossible to know ahead of time until it starts unfolding. But we did have signs that this would be a big event, and, you know, it looked like another time when we had really high helicity values was the November 2002 event where we had the tornado in Mossy Grove. I don't know if you remember that, but that was back in November. So we had an idea that it was going to be, you know, a significant event, or had the potential to be. And a lot of times when these supercells interact with boundaries, you know, like cold fronts, or we had a lot of thunderstorm activity that came in early in the morning, and it probably laid a lot of outflow boundaries around the area, because these thunderstorms produce like miniature cold fronts. You know, we call it the outflow boundary from the thunderstorm. So I think we had a lot of boundaries across the area, and that might have been one of the reasons why we had such a very efficient event. You know, the supercells were very efficient at producing these tornadoes. So I just wanted to touch on some of the science behind this, and I think we're going to go ahead and have David Holtz and Tim Doyle talk about the radar presentation. We'll show you what it looked like from the radar perspective and how we try to warn for these storms.